welcome to Mathematics with Tom. I am Tom, and today we're going to take a look at how to diagonalize the matrix of A. So let's use this example. Let's say that A is the matrix of 0.6, 0.4, 0.5, 0.5. So this is actually a special kind of matrix. It's called a Markov matrix, and it has the unique property that each column sums to 1. Those often represent probabilities of some kind of event. Well, in this case, what we're going to do, though, is we're going to diagonalize A. So what that means is we're going to write A as the V, the matrix of eigenvectors, times lambda, the diagonal matrix of eigenvalues, times V inverse, which is obviously the inverse of the eigenvector matrix. So here we go. The first thing we want to do is we need to find the characteristic equation, and we know we've practiced that. That arises from lambda squared minus the trace, which is 0.6 plus 0.5 times lambda plus the determinant, which in this case is 0.6 times 0.5 is 0.3 minus 0.4 times 0.5, 0.2, and we're going to solve it when that is 0. Let's clean this up. Lambda squared minus 1.1 lambda plus 0.1 equals 0. And it looks like that'll factor to lambda minus 0.1 lambda minus 1 equals 0. So we can say lambda 1 is 0.1 and lambda 2 is 1. All right, so now let's find the associated eigenvectors. So when lambda 1 is 0.1, then what we're going to take is we're going to have lambda minus 0.1 times I. Well, that's going to be 0.6 minus 0.1, that's a 0.5, 0.5, 0.4, and then another 0.5 minus 0.1, 0.4. And there we go. Notice that the second row is just a multiple of the first row. And in other words, this is going to say, you could row reduce that if you wanted, but what you're going to find out is that x1 is equal to minus x2. In other words, that gives rise to the first eigenvector of minus 1, 1. You could choose others, but let's use that. There. Now, our next eigenvector is going to come from when lambda 2 is equal to 1. All right, so in that case, we have a minus 1 times I. That's going to be a 0.6 minus 1 for a minus 0.4, and then a 0.5, and then a 0.4. And 0.5 minus 1 is minus 0.5. And again, you can see that a multiple of negative 1 is the difference between these. And so what this says, though, is this says that negative 0.4 x1 is negative 0.5 x2, or we could say that x1 is 5/4 of x2. So using that, let's use our second eigenvector. So v2 would be 5/4 1, but I could use x2 as 4, so that would be 5, 4. And now I can write v. So v is, and I'm going to put these in order. The first eigenvector is minus 1, 1. The second eigenvector is 5, 4. And now, when you enter these into lambda, well, they have to be in association. So for the first eigenvector of negative 1, 1, we have to put in the associated eigenvalue, which was 0.1, 0, 0. And for the second eigenvector on the diagonal, that arose from 1. And we can find V inverse. Well, remember, we found this. You switch the diagonal elements. So this is going to be 4 -1, and then you change the sign on the anti-diagonal, -1 minus 5. And then you multiply it by 1 over the determinant of v. Well, that's going to be a -4 minus 5 times 1, or -1/9. Now I can write a. A is equal to v, which is -1, 1, 5, 4 times lambda, 0.1, 0, 0, 1, times v, which is 4, -1, -5, -1, times -1/9. Now, so that is a. But now let's remember, we said that the beauty of diagonalizing a matrix is that a raised to the k is equal to v, the eigenvector, times the eigenvalue matrix raised to the k times v inverse. And the beauty of raising the diagonal matrix to the kth power is that all it affects is just the diagonal entries are raised to the kth power. So let's find out, what is a to the k? So a to the k is going to be, this doesn't take some work, so here we go. It is -1, 1, 5, 4. Okay, don't let me make a mistake. Times 0.1 raised to the k, 0, 0, 1 raised to the k, which remember, k is, that's just 1, times 4 -1 -5 -1 -1/9. So that is equal to, I'm going to work with the left two matrices, and let's see what we get. So I have -1 times 0.1k. So that's going to be -0.1 to the k plus 0. Okay, then we're going to go row 2, column 1. Well, that's going to be 0.1k plus 0. And now we're going to go row 1, column 2. Well, that's going to be 0 plus 5 times 1 to the k, which is, but 1 to the k is 1, so that's just plus 5. And then row 2, column 2, that's going to be 0 plus, that's going to be 4. Okay, times v inverse, which is still 4 -1 -5 -1 to the -1/9. All right, now we just have to finish this multiplication. So this is equal to, this is going to be a -4 times 0.1 raised to the k, so row 1, column -5. And now I'm going to go row 2, column 1. So that's going to be +4 times 0.1 raised to the k -4. And now my next one, let's go row 1, column 2. That's going to be that's going to be a plus 5 times 0.1 raised to the k. Row 1, column 2. Okay, -5. And now row 2, column 2. So that's going to be -5 times 0.1 raised to the k -4 times -1/9. Now, there it is. That's a lot of work. But there we found this is a raised to the k. Well, now, what if you wanted to take k to the 10th? Well, you could just plug in k as 10, and you'd have an answer. If you wanted k to the 11th, you could find that as well. But what happens, notice this, though. Notice that one of the eigenvalues was 1, and those just became 1. But the other eigenvalue was 0.1. So each time I raise 0.1 to another power, it just moves the decimal over one more place. Well, it doesn't take long, and fairly soon, 0.1 raised to a large number is effectively 0. So let's find out what happens as k goes to something large like infinity. Then, well, let's see, a infinity would equal, well, 0.1, so let's look at each entry. 0.1 to the infinity is 0, so my first entry is just minus 5. Then my row 2, column 1 entry, again, I'm going to have 4 times 0 effectively, so that's going to leave me with a minus 4. Now when I work on row 2, column 2, I'm going to have 5 times 0, or this would be a minus 5. And row 2, column 2 is going to be a minus 5 times 0, minus 4 times negative 1/9. And I'm going to clean this up. My final step is a infinity is going to be 5/9, 4/9, 5/9, 4/9. And there it is. Look at this again, a Markov matrix. As you progress, it reaches a steady state. So whatever this is describing, the steady state is 5/9 of one and 4/9 of the other. This is the steady state. And it's the motivation for why we want to diagonalize a matrix, is because now we know in advance the final, whether a system is going to reach an equilibrium or if a solution will not have an equilibrium. I hope that helps, and thanks for watching.